Hi everyone. So I'm going to discuss a little slice of my research. I'm looking at cilia and in particular doing biomedical imaging to try to quantify some of the observations that we're making. And specifically we've been making heavy use of Spark because the data sets that we're working with have exploded to be rather large. To give you a bit of a quick background about myself, so I'm a Georgia Tech alumnus with a computer science degree who went off to mix computer science with biology and then got hired by his arch nemesis. And so now I have one of those house-divided license plates on my car. And now I spend all of my time researching in imaging, as it relates to public health, a lot of data science, a lot of open source programming, a lot of running. I've done quite a few marathons, and that's fun as kind of a testing ground for some of these methodologies that I'm doing. But this project in particular deals with so these microscopic hairs called cilia. You may have encountered these before in some of your grade school biology classes. Cilia are the microscopic hairs that line your throat, your nose, your brain, your lungs, your kidneys, and just about anywhere where there's any kind of fluid. They beat in these regular synchronous waves that you see here in this video example in order to move particulates out that might cause irritation or other problems and move nutrients in and generally just keep things moving smoothly. If you were to cut one of these cilia open, you would see a structure along the lines of what you see here in the bottom right. It looks kind of like a bicycle wheel complete with spokes. So there are hundreds of different proteins that go into making a single cilium. And so whenever you have some sort of a genetic disorder that impacts how these cilia are constructed, or some sort of secondary disorder that affects how the cilia are constructed, you get what's known as a ciliopathy, where since they're not constructed properly, they don't beat properly, which means you get all kinds of nasty secondary symptoms. And I'm getting kind of ahead of myself here. So why we care about cilia. I have two videos here. The top is what normal motion looks like. So everything looks like it moves fairly uniformly. You see kind of a wave moving along the cell wall. And on the bottom, I swear there's actually motion happening there. It's an extreme example, granted, but very little motion. This is a classical ciliopathy. There's very little ciliary motion. Nothing is moving around. Everything's getting clogged up. And you have a lot of clinical issues associated with these sorts of conditions. As we're beginning to discover, there are also developmental consequences. There's a lot of preliminary research out there that suggests many of the cells in early development stages specialize because of signaling that happens when the embryo is rapidly dividing, and some of this research points to cilia as generating the fluid flow that in effect creates that signaling and therefore the cellular differentiation. I'll get into this a bit more later in the talk, but these are sort of the broader implications of why we want to study this motion, what it could potentially tell us from a clinical and diagnostic perspective. So then the next question is, how do we diagnose ailments of the cilia? As with most things, there's a spectrum of methods ranging from fast and cheap but inaccurate to slower, more expensive, and of dubious accuracy nonetheless. On this far end of the spectrum, we have a technique known as measuring nasal nitric oxide levels. You literally measure how much nitric oxide comes out of someone's nose when they exhale. For whatever reason, and the research is not clear on this, there is a correlation between high nasal nitric oxide levels and ciliopathies. The reasons are still unclear, but this leads to a lot of false positive rates. And so this is generally done as just kind of a first step. The next step would be the computation of ciliary beat frequency. And so you notice these videos kind of lend themselves to some traditional signal processing methods that I'll get into, where we can measure how quickly are the cilia beating. That can tell us something about whether or not the motion is healthy. As you saw in that other video, the bottom one that barely looked like it was moving, The beat frequency is probably close to 1 or even 0. For normal cilia, we find there's a range of about 10 to 12 hertz. But again, there are a lot of false positives there. There are a lot of gray areas. Other conditions that have nothing to do with abnormal cilia can impact the rate at which they beat. So again, that's also not predictable, or that's also not reliable. You'll notice there's a pattern emerging here. Another method, which is one of the favorites actually, is electron microscopy to search for structural defects. As I mentioned, that structure of the cilium, when some sort of genetic mutation impacts how it's built out of the proteins, you can look for that. The problem is you can't get a feel for how it looks when it's beating. And we've also found that there are ciliopathies that express without any structural defects. So you can stick this thing under an electron microscope. It looks perfectly fine, but for whatever reason, it's not beating or it's beating improperly. And so again, not a perfect method. And finally, we have manual beat pattern analysis. And so this is taking a biopsy from a patient, growing it in a petri dish, putting it under a high-speed digital video microscope, and having a clinician look at it. And it's this step that we're focused on because more or less all of these methods constitute the gold standard for ciliopathy diagnosis. Not one of these can by itself identify abnormal ciliary motion, and so they're usually all taken in tandem. I should mention, if there are any questions at any point, please don't hesitate to interrupt me. So what our goal is, given this kind of diagnostic ensemble, it's the gold standard, but it's highly imperfect, is we want to take a high-speed video of a ciliary biopsy, like the ones I've shown you, and output some quantitative properties of the observed motion. The idea being, rather than arguing over what the motion looks like from a qualitative point of view, we can attach numbers to it and hopefully say something much more robust, much more convincing about what we observe. So that's the goal with this research that we're doing. So the strategy that we have for quantifying motion comes from an old computer science adage that says, if you don't know how to solve something, look for a problem that's similar that has been solved, and see if you can shoehorn your problem into that one. And the problem that we're looking at is a class of time series known as dynamic textures. And these are videos that have a regular statistical motion to them, but with some amount of random noise. As an example, I have a video here of grass blowing in the wind. You can also think of water rippling, clouds billowing, trees swaying, flames flickering. These all fall under the category of dynamic textures, and these can all be analyzed more or less the same way. I put this video of cilia here to kind of underscore the fact that, at least from a qualitative point of view, there are some similarities. And so the hope is we use similar analytical methods for classical dynamic textures to analyze cilia. Maybe we'll get something useful out of it. So the general pipeline is we have a raw video and we want to convert it to features, kind of like any machine learning problem. You have your data, and we want to build features out of it. So first we have videos on the far left, and we want to pick out regions of interest. And this is just a pre-processing step to try to cut out noise, maybe some translation artifacts or some particulates that are propagating through the fluid that the cells are suspended in. We just want the cilia. We don't want anything else. This can be done manually. Someone can sit and draw regions of interest over the cilia, but we're also looking at automated methods of doing this because that's far more interesting. Once we have these regions of interest, we compute optical flow. Now, optical flow is a computer vision algorithm that essentially it gives you a vector field. If you remember back to calculus, for each pixel in the video, it looks at, let's take a pixel of a video at a particular frame, and then move to the next frame. I want to then look at the neighborhood of pixels I'm standing in and lay a vector down connecting where I am now to where I feel like I moved to in the next frame. And then do that for every single pixel. for every single pair of frames. And so you get this vector field where all the apparent motion is happening on a pairwise frame basis. It's a nice estimate of kind of what's happening. It has its problems for anyone familiar with optical flow, but for kind of a first order estimate of the motion, it's pretty good. Once we have the optical flow, then we compute its derivatives. So we want to know how is the optical flow changing. And once we have the derivatives, we can compute what we refer to as elemental components. These are essentially first order statistics of the optical flow. And we use these because they have very nice interpretations. They take these nice names and they have these nice interpretations that make it very easy to kind of intuitively understand what's happening. So there's scaling, which is the rate at which things jump out at you or fly away from you. Deformation, which is the rate at which things squeeze and deform or crush and shear. And then we have rotation, which is the rate at which things spin. And so we could have gone with higher order properties, but these had very nice kind of intuitive handles that we could grasp to understand what was happening with the cilia. As you might imagine, for 2D videos, scaling doesn't really give us much. The cilia are moving within the plane of the video. They're not coming at you. They're not going away from you. So this was kind of a useless property. But deformation and rotation were very, very useful. And so for the rest of the talk, you can more or less assume this is how we describe the ciliary motion that we're seeking to quantify. So what do these features look like? Okay, I've described rotation, deformation, but what do they look like in practice? So I'll give you these two videos again, one normal one on the left, a highly abnormal one on the right. And we highlight 3 pixels in each of these videos. Blue is a pixel that's very close to the cell wall. Red is a pixel that is kind of at the tips of the cilia, and black is a pixel that's just out in the fluid. And we can plot, say, rotation in radians per second computed at each of these pixels at each frame. And there is quite a stark difference between the two, especially as you move along the cilia towards the tips. That's the red line, highly periodic. So we see a very nice temporal pattern with quite a degree of rotation, which makes sense. Healthy motion, the cilia is going to bend significantly. There's a lot of rotation happening. I didn't show deformation, but it follows kind of the same qualitative properties. For the abnormal motion, you really don't see much of anything. Again, that's a bit of an extreme example. There's usually some periodicity, but spoiler alert, this is kind of a pattern that we observed. So this is what these features look like. So now that we have rotation, deformation, how do we build a model that we can use to differentiate these motion patterns? So the typical strategy, I shouldn't say typical, one of the favorite strategies to model dynamic textures is actually one, if anybody was at the time series talk yesterday, I believe, you're probably familiar with this. These are autoregressive models. With a slight twist for the dynamic texture aspect. The bottom is probably what you're familiar with from autoregressive models, where each observation t is a function of some number of previous observations and a coefficient. But for the dynamic textures, we first take our rotation or deformation data as modeled by yt, and we project it into a low-dimensional state space using some basis c. You can learn c however you want. It could be wavelets. We used PCA. Fairly straightforward. So we take our high-dimensional rotation data, project it into a low-dimensional state space, then learn the parameters. And it's these motion parameters that are our feature vectors. So we just take each of these they're matrices, they're small matrices. We squash them, concatenate them together, and that's our feature vector for a particular movie. To give you an idea of what these look like, the top 5 are parameters from a normal motion ciliary sample. The bottom are from abnormal motion. It's kind of hard to tell if there's anything going on there. So the next step was to simulate this motion. Once we've learned the parameters, we can simulate the motion in the low-dimensional state space. And that's where things got really interesting. So the red is abnormal motion, the red is normal, and the blue is diseased. And what we see is healthy motion has a much larger degree of freedom to move around in this low-dimensional state space. The blue abnormal motion just tends to stay right around the origin in a very small bubble. And in fact, with only about 1 or 2 dimensions of the state space, well, it has about 1 or 2 dimensions of freedom in the state space. It doesn't go into any of the other dimensions. The normal motion in red goes all over the place. We needed a lot of dimensions to model its motion accurately. And so with that, we could build a binary classifier that got 93% accuracy, which isn't bad. Great, but this has a lot of flaws. The most glaring of which is how we actually set the ground truth. How do we come up with this 93%? Well, we have people look at the videos and say whether it's normal or abnormal, which is kind of, we're judging our model's performance against the very subjectivity we're trying to eliminate with this pipeline. And so that's one problem, but that's actually only a subset of the biggest problem, that there are definitely more than 2 types of motion. Right now we're just classifying things in normal and abnormal, but it is widely accepted that there are at least 4 kinds of motion, if not more, probably more like 10. These are 4 canonical examples of motion patterns that most people will agree on, at least in terms of them being different. As for names, that you can kind of pull out of a hat. I've heard some people refer to the top left as incomplete, the top right as dyskinetic, the bottom right as wavy. As for why those names are applied, I have no idea. They're certainly not based on any sort of quantitative properties. They're based entirely on the training and experience of the specific clinician. And so there's absolutely no cross-institutional relevance. You cannot have confirmatory studies that span multiple institutions. And so any kind of large-scale study using the results of any multiple individual clinics is all but useless if you want to do anything other than basic normal, abnormal. And even within that, it can be difficult. So this is easily the most glaring weakness. We know there are everybody agrees there are more than 2 types of motion. Any clinician you ask, oh, absolutely, there are more than 2 types of motion. How many are there? Don't know. What are their names? I don't know. What characterizes wavy versus dyskinetic versus incomplete? I don't know. And these subtypes have important clinical implications. The reason is that most of these motion subtypes can often be indicative of very specific ciliopathies or associated disorders. There's primary ciliary dyskinesia, which is kind of the big genetic disorder that it's a genetic mutation that directly affects the cilia themselves. And so that's kind of an outlier. But there are a lot of other disorders that are highly correlated with ciliary dysfunction that we're only just starting to scratch the surface of. Congenital heart disease, heterotaxy, situs inversus, where you have the organs reversed on which side of the body they're on, cognitive defects, developmental defects, and these all go back to the fact that cilia are being implicated in the early stages of cell signaling and differentiation. And so this delves into a lot of different areas where the specific motion subtype could tell us a lot about the disorder. But without any sort of quantitative method, there's no way to be sure. So that's what we're trying to do now. So the question then becomes, is there a way where, not knowing a priori how many, sorry, I almost gave the answer away, how many motion subtypes there are, or what they are, is there a way that we can learn these latent patterns? And the short answer is yes, using clustering. We can stick with the same model, the autoregressive model that we had before, where we learn these AR parameters for each sample, each region of cilia. And then we cluster these to try to find discrete motion patterns that are similar. This is a very nonlinear space, and so we have to look into geodesic distance metrics, which means just throwing k-means at this, which is a nice scalable parallel algorithm, is out of the question. We need more sophisticated algorithms. And in addition, whereas in the classification study I just showed you, the 93% binary accuracy, we had about 291 videos, or what is that, about 80 patients. For unsupervised subtyping, we have the 291 from the previous study, 431 that we left out because of some reason, usually a recording artifact, but now which we're going to put back in. 628 that we've collected from our internal collaborators, and over 1,000 from collaborators around the world. If we're talking about, they're about 200 megabytes per video, and so we're already looking at half a terabyte of data. For clustering, we need a lot more data in order to come up with a reasonable estimate of how many motion subtypes there are. And so this, finally, is where Spark comes into the equation. As kind of an aside, we have this lovely website that we've been using to acquire data from our internal and external collaborators. Very easy to just upload a video. It even lets you draw regions of interest if you are so inclined. But we also have an automated method of doing the same thing. And now to quickly go over, so this is then where Spark comes into play. So the general pipeline consists of 3 steps. First, we want to pre-process the videos. And that involves identifying regions of interest. And so for each video, which is our raw data, we are doing a flat map to find regions of interest. And this depends on things like how much motion we see at each pixel, how much motion we see at surrounding pixels. Sometimes we run texture filters to get an idea of whether or not we're looking at a cell or some cilia. A lot of different strategies that we can do here. And this gives us back an RDD of regions of interest. And this is usually 10 to 20 times the size of the original RDD, since we usually will pull in about 10 to 20 regions of interest per video. And then for the regions of interest, we compute all the flow features. And so this involves computing optical flow, computing the derivatives, and then computing rotation and deformation. And not only do we use Spark, but for the various independent operations, things like OpenCV to do the optical flow, scikit-image to do some of the feature detection, for video registration, and for just finding the regions of interest in the first place. So now we have all the regions of interest. And we want to derive the autoregressive subspace. So this entails principal components. That's what we need our basis in order to take the high-dimensional rotation deformation data, project it into the low-dimensional autoregressive state space. And for this, we do an SVD computation, broadcast those components, and then for each individual region of interest, we can compute the AR motion parameters. So for each region of interest, we have D parameters that are each usually 5 by 5, 10 by 10, something along those lines. Use SciPy for most of the basic linear algebra computations, but for the distributed SVD, we use something out of Genelia Farms called Thunder, which is a wonderful Python package built on top of Spark that has a lot of distributed linear algebra operations. It's very, very nice. And now that we have our AR model parameters for every region of interest, we want to do clustering. And in order to do clustering, first yes, sorry.
Sorry, on the PCA?
Yes.
So on your slide you have YT equals CXT, if I remember correctly. So
yes.
Are you doing the PCA on the old time series, or are you doing the PCA for a specific time?
So the question was, are we doing PCA for all of the data or for one individual time series at a time? And that is a really good question because we found something very interesting when we did that. The classical approach is you have to concatenate all the time series together and do SVD on the entire data set. So you get the global basis. And what we found was, because this is kind of I can explain later in more detail, this is sort of a special case of dynamic textures where everything shares the same subspace. That's not usually the case. When you're trying to differentiate dynamic textures, usually everything has its own subspace. because you're trying to differentiate, say, rippling water from billowing clouds. Those live in different subspaces, but here everything lives in the same subspace. We found that even though we did a global SVD, and that's why we use Thunder, we want to do an SVD on the whole data set, we found that we could still pretty well approximate it by the local SVD of a single time series. Just empirically speaking, it worked. But nonetheless, we went with the global SVD. So once we have the AR parameters, the next step is to, since we're in a very nonlinear space, we can't just do straight up Euclidean distance. We first need to do some sort of pairwise comparison. So this is, say, building a graph where first we compute the pairwise similarities between each, and I'm showing this Cartesian operation where we're essentially mapping every pair of AR parameters to every other pair. This is not what we do in practice, but this is just to illustrate. And then once we have each pair of AR parameters, we use, say, the most common operation would be a radial basis function, compute some level of similarity between the two. Again, we do something a bit more sophisticated, but that would be one way of doing it. And then once we have this graph, which is essentially a Laplacian, then we can do an SVD and find its principal components. And that gives us sort of the low-dimensional feature space of these AR parameters in which they are now linear, and we can do something like k-means. For the pairwise distance comparisons, we use scikit-learn. And again, just to repeat, this is not something you want to do when you have a couple million data points. You do not want to Cartesian it with itself. You'll be sitting there for quite a while. In practice, we use something like locality-sensitive hashing, or perhaps some sort of Nystrom sampling method, where we have a small kernel of data that we use to sort of extrapolate what similarities we should compare. But yes, only use Cartesian for very, very small data sets. And so, okay, what we found was for a small sample of our data set, we visualized a very small sample of it in three-dimensional space after we did the SVD computation of the graph Laplacian and projected it all into this three-dimensional subspace and colored it based on whether or not it was normal, in this case blue, or abnormal red. We found that there is a definite spectrum within this low-dimensional space where all the abnormals tend to reside again around the origin, but as we move outward, there's a progression from abnormal to healthy motion. Again, not enough data here in this first pass to really say if there are discrete clusters, but there is a definite structure to this subspace where we can say these are clearly the most abnormal, and then we progress to more normal motion and eventually get to sort of the definition of healthy motion. And so this is kind of where we are now with our analysis. So we have a 93% classification rate between normal and abnormal, so we know this dynamic texture representation works. We have this definition of a low-dimensional embedding of autoregressive parameters, but it's definitely more complicated than just a binary normal-abnormal distinction, which means we need a whole lot of data. And the ultimate goal is we want to create a black box tool for clinicians. There are lots of clinicians out there who would love this sort of information, but don't care to know anything about Spark or distributed machine learning or autoregressive models. And so we're working on, I showed you screenshots of a web front end with the Python middleware and a Spark batch processing backend. The idea being they can upload a video and get diagnostics and analysis. And we're working on kind of incorporating some expert input, annotating phenotypes, adding regions of interest. And with that, that's kind of the summary of my work, at least in this area, and I'll take any questions you might have.
Awesome. So we have time for about 2 questions right now, so very quickly.
Hi. Did you look into Fourier transforms and maybe Gabor filters. Gabor is somewhere between space-time and frequency. Fourier is exactly in frequency domain. Did that give you any results?
So there is a whole part that I kind of skipped over where we looked at the frequencies that were present in all of these signals. And remember, I mentioned that so healthy motion has kind of this large degree of freedom within the state space, and unhealthy motion has this kind of very compact presence in the state space. In the Fourier domain, it's the opposite. We found normal motion tends to have a very dominant single frequency and very low power at everything else, whereas abnormal motion has power across all the frequencies. And so I didn't mention that here, but yes, we've looked at it and it's extremely interesting. Gabor filters we haven't quite got to yet. We're thinking of using filters as a replacement, a drop-in replacement for the definition of the basis. Rather than using PCA, we could just do filter responses.
Any more questions? All right.
You can hear me now. Okay, yeah. So I checked out the Thunder package just while you mentioned it, and it seems like there's not, I mean, some of scikit-learn is supported, but not like everything, right? Do you have there been limitations on methods you've tried, like say the clustering, just because of the sort of limitations for Python on the Spark platform?
So at the moment, I believe Spark support, the native Spark Python support includes a distributed matrix representation, which actually when we started this also didn't exist, but Thunder has one. But it's still right now missing an SVD implementation for the Python API, which is again why we're still using Thunder. But as for clustering, once you're in that low dimensional space, then you can finally throw k-means at it, and that's where we can go back to the native Spark library.
Awesome. We have no more time for questions, but let's give a big round of applause to Shannon.
Thank you.
And that wraps up the research track.